This is important. This is what we're doing today. This is an absolutely simple problem except for one thing. What goes on in the tubing. And that's what we're talking about most of today. As you will see, the mere transport of a narrow zone of analyte or solute or whatever through an open tube, no chromatography going on, causes rather considerable broadening of that narrow zone. And in this case of a 5 centimeter HPLC column, et cetera, et cetera, et cetera, you're going to see that it actually increases the apparent width of the peak quite a bit. I can give you the equation for that now, but you won't understand why at all. Today is about why does this happen. And the basic reason why it happens has to do with the physics of flow in a cylindrical open tube. That's the whole issue. And this takes place in every piece of connecting tubing, in every chromatograph, in every capillary electrophoresis instrument in the world. And in gas chromatography, it's not a big issue because diffusion in gases is fast. In liquid chromatography, it's a very, very big issue because diffusion in liquids is 4 to 5 or perhaps even more orders of magnitude slower than in gases. So with that said, let's get into the physics of flow in open tubes, meaning unpacked tubes. There's no particles in the tube. And we'll see that this leads to something which is known as Hagen-Poiseuille flow. Did anyone here go to the Kolthoff lectures last week? Monday, maybe? Monday, she spent about 2/3 of her time talking about exactly what I'm going to talk about right now. It's that big of an issue. It's still an issue that is a research issue. This is going to lead us to the mass conservation equation in an open tube. And that in turn, that mass conservation equation can be solved, and it yields an equation known as the Aris-Taylor equation for dispersion in an uncoated tube. It has important chromatographic consequences even though the tube is not coated, because all the connecting tubing we use is uncoated tubing, and you get broadening even if you're not doing any chromatography in the tube. Subsequent to the work of Aris, by the way, Aris was a professor of chemical engineering here. He was a really fine fellow. He was actually a student of Taylor. Taylor and Aris both were world-class hydrodynamicists. If you know any of the history of the atom bomb, you'll know that a major breakthrough in designing the first atom bomb was the development of what was called an explosive lens. It was a lens, it was explosives that were set off in such a way as to have a symmetrical force field applied inward, which is what caused the plutonium to come in contact with enough other plutonium to reach critical mass and explode. The guy who worked out the hydrodynamics of that was Geoffrey Taylor. He was a really excellent physicist and applied mathematician. And he worked on the problem that we're going to consider today. And we'll look at the chromatographic consequences of this dispersion in uncoated tubes. And then the result that we're interested in for the purpose of chromatography was first developed by Marcel Golay. And that is, he developed an equation for the HETP in what we call open tubular chromatography, gas chromatography, specifically the device I showed you last week. He's the guy who basically figured out what the HETP in that thing should be. Has anybody ever heard of Golay before? I expect there's at least 2 other guys who've heard of it. Sure. Golay invented the first really decent, he was a brilliant guy. He was an electrical engineer, had no chromatography background whatsoever, none, zero. He invented capillary chromatography. He invented the first decent detector for IR spectroscopy. That was in the middle 1950s. Before that, they used these kludges, very, very insensitive, terrible sensors. IR spectroscopy didn't really become a practical analytical method until the middle 50s when Golay developed his IR detector. If you take Phil Bullman's signal-to-noise course, you will absolutely hear about the so-called Savitsky-Golay filter. That was also another invention of Golay's. If there was a Nobel Prize for engineering, this guy should have 3 of them. It's a fantastic guy. Okay, so there's our friend the capillary, and there's the Taylor-Harris dispersion equation. It relates the dispersion coefficient, which is an effective diffusion coefficient for longitudinal dispersion, axial dispersion if you want, in an uncoated tube under laminar flow conditions. We're going to have to talk about laminar flow. This equation is called the Harris-Taylor dispersion equation. And you can see that the dispersion coefficient is equal to the good old molecular diffusion coefficient plus a very important term which depends on the radius of the open tube, the average velocity in the open tube, and inversely on the diffusion coefficient again. So there's a very complicated dependence here of the effective dispersion coefficient on diffusion. Diffusion acts both to increase dispersion and to decrease dispersion, because the bigger the diffusion coefficient is in the second term, the less the second term counts. So it's a complex process. This term clearly is driven by flow. If we set the flow equal to 0, we have only the first term, which is a pure diffusion event, pure molecular diffusion. As I said, Golay came along a few years later and showed that if you had retention on the wall of the tube, this second term actually gets bigger because of this K prime dependence. And we'll show where that comes from later on. So let's go back to the open tube. Everybody in here has done F equals ma problems until their ears bled in freshman physics, right? This is what you get if you apply F equals ma to a fluid in a tube. It's called the Navier-Stokes equation. It's nothing more or less than Newton's conservation of momentum equation as applied to a very specific kind of fluid. In this case, it's what's known as a Newtonian fluid. And I'll leave it to your imaginations as to where the name Newtonian came from. But it means a fluid whose viscosity is independent of velocity, of how fast the fluid is moving. This is the viscosity coefficient of whatever fluid we're talking about. In terms of the fundamental physics here, The left-hand side, this is the density of the fluid, which is equivalent to the M term, the mass term in the equation. So this side represents all of the inertial forces per unit volume in the fluid. The right-hand side are the driving forces and the dissipation forces that take place in the fluid. The dissipation of the momentum happens through the viscosity. The viscosity is like friction. It's friction among the molecules comprising the liquid. It is the sum of the divergence of the stresses, meaning the pressure, and the viscous drag, plus what we call the body forces. So gravitation, centrifugation, any other force that you can think of to apply to the fluid is gathered together in this capital F. Well, the situation that we are interested in specifically now is the steady state solution of this equation. That means the time independent part of this equation. That means that this term is 0, du dt. U is the velocity of the fluid. So if it's the steady state solution, du dt is 0. We're applying it to an incompressible fluid, so theoretically this has to be not a gas, but a liquid, and not just a plain liquid, but a highly incompressible liquid. We have to disallow any heating of the fluid during the flow process. It has to be a Newtonian fluid, meaning the viscosity is independent of velocity. The tube has to be horizontal. It has to be like so, not like this. And if it's horizontal, then gravity doesn't matter. And we have to assume that, I hope I said this, I didn't say it, you're not somehow rotating the tube about its axis. And that wipes out centrifugal forces. And that means that term is 0. Now here's the big one. You have to assume laminar flow. And under laminar flow conditions, this times that is negligible compared to that term. Say it again. Under laminar flow conditions, all of the inertial factors don't amount to anything compared to the viscous factors and the pressure that you apply to the fluid. So it is the pressure that you apply that makes the fluid flow in the horizontal tube. If you had a vertical tube, it could, of course, under the force of gravity, induce flow. We're going to get rid of that factor. We don't need to worry about it in the problems we're interested in. So it turns out that this equation was then solved for the case of a cylindrical tube, not a square tube, not a rectangular tube, not a slit, but a circular tube by Hagen and Poisson. And what they found is that there's really only one kind of velocity, and that is that there's velocity in the direction of the tube. And they found that the average velocity in the z direction, so the tube is like that, and that's the z direction, that velocity is equal to 1 over 8 r squared, the radius of the tube, times the pressure, which is the driving force, but it's the pressure per unit length. It's not just the total pressure, it's the pressure gradient, the pressure per unit length. And it depends inversely on the viscosity. So the lower the viscosity is, the more flow you get for a given pressure gradient. The narrower the tube is, the less flow that you, the narrower the tube is, the higher the velocity is. However, excuse me, I'll get to the however in a second. Your total flow, this is your volumetric flow now, U is your linear velocity. The total flow then would be equal to the average linear velocity, U bar, times the area of the tube. It's a circle, so it's pi r squared is this area. So your total flow is pi r squared times your average velocity. And you calculate the average velocity given the pressure from the Hagen-Poiseuille equation. But there's one more part to this that really is absolutely critical, and that is the fact that the velocity, the z velocity, is not independent of distance from the wall of the tube. It has a quadratic dependence, a square dependence, on the distance from the center of the tube. So there's the tube. That's the radius of the tube. So this is plus r, and this is minus r. And then right in the middle of the tube, we have r is equal to 0. But if we set little r equal to big R, we get a 1. 1 squared is 1. And we have 1 minus 1 is 0. There is no axial velocity at the wall of the tube. The fluid right adjacent to the wall under what we call the no-slip boundary condition is 0. The fluid a little bit in from the wall is moving. As we go in further and further, and when we get to the exact center of the tube, and we set little r equal to 0, then we find that that the velocity at the center of the tube is equal to 2 times your average velocity. Now, imagine a molecule of anything right smack up against the wall. According to this result, its velocity in that direction is 0. But a molecule right dead center of the tube, its velocity is twice the average velocity. So that's supposed to be a diagram of the velocity of the molecules as the distance from the wall of the tube, and it forms a parabola. This is under the condition, the laminar flow condition, which we assume for the Navier-Stokes equation to be solved. Now, I'll come back to that in a minute, but we have to look at viscosity for a little while, so you get some appreciation for what I'm talking about here. These are the 3 most common gases used in gas chromatography: hydrogen, helium, and nitrogen, measured in units of micropoise. Okay, so we're looking at numbers on the order of 100 micropoise. It's interesting And important to note that the viscosity of hydrogen, let's take 200 degrees as being a typical GC temperature. Certainly 0 is not a typical GC temperature. But there are people who do subambient GC. And so you might occasionally get to this kind of temperature. But if we compare hydrogen and helium, there's a substantial difference. I'm sorry, that's 300, there's 200. There's a substantial difference in their viscosities. Also notice somewhat unintuitively that as you warm a gas up, its viscosity increases. And nitrogen, as being a lot heavier than either helium or hydrogen, nitrogen has a substantially higher viscosity. These are common liquids that we encounter in the real world, water being the most common. The viscosity of water at 20 degrees centigrade atmospheric pressure is 1 centipoise, 1/100th of a poise. The gases were 100 micropoise, that's 10 to the minus 4. This is 10 to the minus 2. That's a factor of 100 in viscosity. Clearly, pumping a gas is going to require a lot less pressure than pumping a liquid. Other interesting thing about liquids is their viscosities invariably get lower as you increase their temperature. And water at its boiling point still has liquid water, not the gaseous form, but the liquid state of water has a much, much higher viscosity than does gaseous water at the same temperature, because the density of the liquid phase is a lot higher than the density of the gas phase, so the molecules are a lot closer together. And there's a lot more interaction between the molecules when they're closer together than when they're in the gas state. But your typical organic liquids really have considerably lower viscosities than water, especially things like acetone and benzene and diethyl ether, which are common solvents in chromatography. You'll never see a liquid chromatographer use ethylene glycol, at least not a sane one. Although they might add a dab of it in a mixture as a dilute solution, because ethylene glycol might have just the right solvent properties, but you'll never see it used as a solvent in real analytical work. So this is the ultimate source of what we're talking about, this extra broadening factor. If we have what's called an inviscid liquid, INVISICID, inviscid, non-viscous liquid, there's no problem. There's no problem with if there's no viscosity. But even gases have viscosity. Now, the Hagen-Poiseuille equation applies under laminar flow conditions. Laminar flow is where the viscous forces are much, much bigger than the inertial forces. Turbulent flow kicks in, starts to happen, when the inertial terms in the Navier-Stokes equation, which we neglect, become substantial. That means we're at high velocity. And under turbulent flow conditions, the flow doesn't look like this anymore. It doesn't look parabolic. It starts to flatten out. And you have to get to extremely high velocity conditions in order for it to flatten out even this much. But this has been drawn to represent pretty closely what goes on under turbulent flow. And that is the radial differences exist only right close to the wall, and in the middle of the tube it's essentially flat. Some people refer to this as ideal flow, that is inviscid flow, and here everywhere in the tube, the fluid has the same exact velocity. Chromatographically, this situation is ideal, as you'll see in a minute. Also, the equations for relating pressure and velocity change between laminar and turbulent flow. Down here at low velocity, in this regime, the pressure is proportional to the first power of the average velocity. So if you double the velocity, or you double the flow rate, the pressure doubles. Or to say it another way, if you want to double the velocity, you have to double the pressure. But as you go to higher and higher velocity, this nice linear proportional relationship begins to disintegrate. And it curves over in this region, and ultimately it approaches this relationship, which is velocity to the 1.75 power. Which means that if you want to double the velocity, you have to increase the pressure 2 to the 1.75 power. So it costs you more work to achieve the same flow rate. Almost never in chromatography do we get out of the laminar flow region. There are some special circumstances where it happens. They are very unusual. I wouldn't worry about them. There are some other things that go on when we make the transition from laminar flow to turbulent flow. Here's a plot of the velocity at one point in a liquid versus time. It's very flat. It doesn't fluctuate much. Any natural disturbances in the flow very rapidly dampen out because viscosity is so high. You're in extreme dampening conditions. As you get to the onset of turbulence, if something perturbs the flow of the liquid, you'll get these intermittent bursts of turbulence that dampen out. However, when you're in fully developed turbulent flow, the velocity at a given point becomes perfectly random. This is truly a good random noise generator if you ever want one. So this is absolutely unsteady flow. So there are two consequences, or three consequences then, of going into turbulent flow. Number one, the parabolic profile flattens out. Number two, it costs you more pressure to increase the velocity than under laminar conditions. And number three, the velocity at any given point in the system is no longer quiescent. It's no longer time independent. It's very randomly time dependent. The other thing I wanted to point out is we assumed the steady state solution, meaning things no longer vary as a function of time. Well, at the entrance to a tube, you're not immediately in steady state. It takes a while for the steady state to develop. And this is what we call the entrance length condition. So that at the very, very, very front end of the tube, the parabolic flow has not been fully developed yet, and it looks a lot flatter. And then as you progress into the tube, finally the two boundary layers from the two walls come together, and you're in fully developed laminar flow. And then you have your parabolic flow profile. For the conditions that we're going to be concerned with in narrow tubes, we're not talking about pipes that you can walk through. Engineers do get concerned about those, but we're not. It's very, very, very short. So we can assume that we're always in steady state flow. This is another plot of the entrance length, and it shows how the pressure varies with distance until the laminar flow is fully developed, and then it becomes linear with distance. But during the onset of the laminar flow, it's a nonlinear distance dependence. The principal physical quantity that controls whether you're in laminar flow or in turbulent flow is a number called the Reynolds number. And the Reynolds number is defined for a tube as the product of the average velocity times the diameter of the tube divided by the ratio of the viscosity of the fluid to the density of the fluid. Essentially, this number is dimensionless, and this specific ratio is the ratio of the inertial forces to the viscous forces. So if you have a low Reynolds number, it means that the numerator here, the inertial effects, are much, much, much smaller than the viscous effects. So again, it's saying that the Navier-Stokes equation is being dominated by the viscosity term, not by the inertial term. This quantity, eta divided by density, shows up an awful lot in engineering and in flow problems. And it's given a special symbol at eta star, and this is called the kinematic viscosity. If you work out the units, and you'll have to trust me on this, you use CGS units. Kinematic viscosity has units of centimeters squared per second in CGS. Diffusion coefficients in CGS have units of centimeters squared per second. So this ratio is dimensionless. And the engineers have given it a name. They've named it after Dr. Schmidt. And it's a measure of the rate of transfer of momentum relative to the rate of transfer by diffusion. So it's a momentum, it's a convective thing versus a diffusive thing, if you want to look at it that way. Gases and liquids have very, very different Schmidt numbers. That's sort of obvious. This is the kinematic viscosity, that's the diffusion coefficient. Turns out that Schmidt numbers in liquids are a lot bigger than Schmidt numbers in gases, because diffusion is 4 or 5 orders of magnitude smaller in liquids than in gases, and viscosities I just indicated to you is about a factor of 100 lower in gases than in liquids. So these run on the order of 1,000 for a liquid and on the order of 10 for common gases. But it's an important difference in their properties. By the way, supercritical fluids have Schmidt numbers intermediate between liquids and gases. And I really don't remember whether they're closer to gases or to liquids. I think they're closer to gases, but they're intermediate. Okay, one of the reasons for telling you about the Reynolds number right now is that this is the entrance length and this is the diameter of the tube. And the entrance length is going to be equal to about 0.06 times the Reynolds number. As we'll see, Reynolds numbers seldom, if ever, get above 10. So the ratio of the entrance length to the diameter of the tube is about, let's say, 0.06 times 10.6, call it 1 tube diameter. Well, if we're talking about a tube that's 30 centimeters long and 0.01 inches in diameter, I mean, 99.999% of the tube is in fully developed laminar flow, and only 0.01% is not in laminar flow. Who cares? Right? So you immediately can assume that the Hagen-Poiseuille equation is correct. So I'm trying to defend the solution to this problem right now so that it's not coming out of thin air. So now, let's go back and think about what goes on in fully developed laminar flow. If I have a bunch of molecules all lined up in a nice narrow zone at t equal to 0, and then I allow laminar flow to happen with the parabolic flow profile, this narrow zone, a short time later, will become greatly distorted. And it will plot up like that. So I now have molecules of solute spread from here to here. The zone has gotten a lot wider. If I give it some more time, the zone gets wider still. This is a chromatographic catastrophe. Capillary chromatography would be absolutely, completely, totally worthless if this is what happened. The physics are correct. We are saved by radial diffusion of the solute molecules. What's going to happen is that these solute molecules here in the front of the profile are going to look radially towards the walls, and they're not going to see any other molecules of the same type. There's the concentration gradient, right? What has to happen? They have to diffuse radially. Which way do they diffuse? Radially. These move that way and that way in random steps according to just simple molecular diffusion. But when they take a random step towards the wall, what's happening to their forward velocity? They're moving into a region of lower velocity. This is good. They're slowing down. We want them to slow down because they're in the front. On the other hand, if we look at the rear end of the peak, the molecules that are stuck on the wall, they look towards the center of the tube. They see nobody of their same type in the center. There's a concentration gradient, and so they diffuse radially. Now they're moving from a position, a radial position of no velocity, towards a radial position of finite velocity. This is good. So what happens is that radial diffusion squeezes the zone back together. Now, if radial diffusion were instantaneous, very subjunctive, you could squish the zone back to an infinitely thin layer again. But it's not instantaneous, and it's certainly a lot slower. So, now, here's the problem we have to solve. We got the parabolic flow velocity bringing molecules into this finite cell, and we got parabolic flow taking molecules out of the cell. you simply do a mass balance in and out. You also have, that's convection in and convection out, and you also allow diffusion in and diffusion out by diffusion in the direction of the axis of the tube. And you also have to allow for radial diffusion because it's not a radially homogeneous system anymore because of the parabolic flow distribution. If you set up the mass balance, it works out to this. This is the rate of change of the concentration of the solute. Remember, there's no stationary phase, so I don't have to worry about the stationary phase, it's the solute concentration. This is just mobile phase solute concentration. So the rate of change of the concentration inside this zone is dc dt. This is the net rate of convection of solute into and out of the cell, just like you did the other day in the mass balance problem I had you work through. This is your longitudinal diffusion into and out of the cell. And this is your radial diffusion in the cell. This last term is what compresses that zone. Now this is an exceedingly nasty, by the way, this assumes it's a cylindrical cell. You'd have to write something different if it were a square cell or a rectangular cell or some other weirdo shaped cell. This is a difficult problem to solve. We've got time, we've got axial distance, we've got radial position. And Taylor said, I don't know how to solve this problem, but I know a really good approximation to make. He said, instead of solving this problem here, I'm going to solve this problem, and it's quite different. He assumes that the cell is homogeneous. So this is the average concentration in the cell. He assumes now that the velocity, he replaces this term with this term, but he uses the average velocity and the average concentration, not the velocity as a function of distance and the concentration as a function of r anymore. And he combines these two terms into a single diffusion-like term. It's diffusion-like because it's partial squared c partial z squared, fixed second law. dc dt equals partial squared c partial z squared times some constant, fixed second law. But he multiplies it not by a diffusion coefficient anymore, but by this dispersion coefficient, which is, he makes a function of the average velocity. Now, in my notes, I go through a 3-page argument which Taylor used to develop this, and If you want, you can study that. Otherwise, you just have to believe that he knew what he was doing. It's an interesting argument, however, so it might be fun to read it. So this now is the dispersion coefficient that we're going to use in this equation. And this equation can be solved. And it turns out that it's not at all hard to solve. And it turns out that it predicts that the peak will be Gaussian. It predicts the time it will take to transport the peak through the tube, and it predicts the sigma squared of the peak when it comes out the end of the tube. So this is the time it takes to get to the end of the tube. Pi r squared L OG, that's the volume of the tube. And F is the flow rate. There's the sigma of the sigma squared of the Gaussian. And so combining the sigma squared and the T naught squared, we can come up with an equation for the HETP. And it says that the HETP of this tube is 2D over U average times R squared times U average over 24 times D, the diffusion coefficient. So this term is due to what process? It's coming from here. This is longitudinal diffusion. If you tell me something is due to diffusion, you're not telling me much of anything. Because we got longitudinal diffusion and we got radial diffusion. We got diffusion in the mobile phase, we got diffusion in the stationary phase. Not here, but sometimes. So if you simply say it's due to diffusion, I have learned nothing. You must qualify it. This is your longitudinal diffusion contribution to your peak broadening in the uncoated tube. This is the net result of the flow-induced dispersion as relaxed, as opposed, as focused by radial diffusion. Not diffusion, radial diffusion. If you want to make the equation really simple, you define a reduced H as H divided by R. Why R? Because there are no particles. And the velocity, the reduced velocity, is the average velocity times the radius divided by the diffusion coefficient. And if you make those substitutions in up here, you get that. That's not a hard equation. This term is due to this. This term is due to that. Now, when we're talking about connecting tubes, 99.99999% of the time, this is going to be true. That the second term is going to be way bigger than the first term. So when we're talking about connecting tubes, let's forget about the first term. Longitudinal diffusion doesn't cause much peak broadening in an open tube. I can then take the second term, that's my sigma squared in distance units, that's my sigma squared in time units, that's my sigma squared in volume units. Okay? Got it? There's your problem. Pick one. Pick the one that makes your life simplest. Pick one that answers the question. Solve the problem, send it to me. I'll put the note, I'll send you this so you don't miswrite it. Okay. Send it to me before Wednesday. Don't send it to me 9 o'clock Wednesday morning. There will be a quiz Wednesday. Okay. There will be an exam next Monday. I sent you pages of equations which you can bring with you. You can add anything you want to it, but you can't bring any books or notebooks or anything else with you to class. You will bring a calculator. If you don't bother coming. That's a hint.